So I'm Patrick for the two people in the class that are here and haven't met me before. So I'm the electronics TA for the class. If you have any questions regarding your systems or anything like that, feel free to send me an email. Just so I know before I get too deep into it, are you guys pretty new to Arduino? You are? Okay.
Yeah, I'm too. I have only architecture background, so I'm pretty new to electronic stuff.
Sweet. No, that's totally expected. Great. So, all right. Before I get into the kits and building, what I'm going to do during the recitation is first we'll start out with a quick Q&A. If you guys looked at the problem set and have any quick questions about it, I could elaborate. And then I'm going to spend the rest of the recitation taking a subset of the kits that we're going to send out to you and building different Arduino circuits and kind of walking you through how to construct the circuit, how I do it, why I do it the way I do it, and some simple code. And I'm going to be leveraging hard a lot of the open source code that's already out there that exists on sparkfun.com and adafruit.com. Because generally, when you're starting out, especially when you don't have an electronics background, that's what you'll do. So it's really important for me to just show you guys how to find those resources, how to use them, and then how to kind of modify existing code, existing infrastructure to kind of get from point A to point B. Great. So before we talk about the kit specifically, is there any specific questions about the problem set? Or are there any specific questions?
I haven't looked at it.
That's fine. Yeah.
Okay.
No. Okay. If you have any questions, shoot me an email. If the question is something that comes up often throughout the class, like if I get multiple emails, then I'll email the whole class the answer. Otherwise, I'll get back to you as soon as I can. Great. So I'm gonna switch my view over. So it's probably good.
Real quick, it looks like we just had Poha join, so that's our last one. Thanks, Poha.
Hey, Poha. So, hey, I'm the electronics TA for the class. As I just said, I'm going to kind of go through a subset of the kit that we have that we're going to send to you guys, assemble a simple circuit from it, but kind of walk you guys through step by step on how to actually do that. So great. Feel free. So I have like a whole structured, like multiple project thing to show you. So I have a lot to show, but feel free to stop me whenever you want, and we could just elaborate on anything that's unclear. But for now, we'll keep going. Let's see if this works. Great. So you guys should all see that. I should be in speaker view for some of you guys, so you could make my screen as large as possible. But great, so this right here is a Sparkfun microcontroller board. So on this, it's you have a microprocessor or a microcontroller, and then you have a bunch of pinouts of it. And what you essentially do is this is essentially the heart of your system. You could simply flash LEDs, read sensors, control a screen. And do just a bunch of different things. And generally, there are two websites out there that are very popular in the maker community, especially for people that don't have, an electrical engineering background. And that's Sparkfun is one, and then Adafruit, ADA Fruit is the other. And so they make a lot of custom boards that makers can take and connect and use without needing too much, electrical engineering background. There's some fundamentals that you should understand, but otherwise, it's actually pretty simple. It looks intimidating at first because you're looking at all these circuits and these boards and you don't know how to connect them. But they, in my opinion, they do a pretty good job at making it pretty simple. So I'm going to switch over to this. And so here is the Sparkfun website, and the board that we're going to be sending you guys is called the Redboard Turbo. It's a very fun name, but So it's this board right here, and so you can see the board and a bunch of details about it. But under documentation, they have a schematic of the board, which kind of goes through like detail, like, okay, on this red board, what's there? There's a microcontroller right here, right there, and it's connected to a bunch of different things on the board. And so on the problem set, I actually have you go through the schematic and kind of poke around and try to explain to me like what these different components are, and try to build some intuition of what they do. But more interesting, I think, and more applicable for you guys starting out is when you get your kits, they have a hookup guide, and they generally have a hookup guide for all their components. And we specifically bought all these components from Sparkfun. So when you get your kit and you're unsure what something is, go on Sparkfun, find it, and then go into documentation, and they have already written for you a detailed documentation of what it is. There's a video, how to connect to it, also how to, like, what an overview of it, what the different pins are, what they mean. And if you're unsure specifics of like, oh, what does, MISO mean and S-clock mean, then they have a separate tutorial for, defining what SPI is and what you use it for, as well as I2C. And I2C Inspired are two different communication protocols to communicate with other devices when they're connected. So it's essentially a language that devices use to talk with one another. I2C is the name for the one that's pretty popular in the Maker community to connect a bunch of devices. It's simple. You don't need as many wires as SPI, but and that's the one we're going to be working with today. So today I'm going to be showing you some code using the Arduino development platform. And when you scroll down here, you'll see how to set it up. And so if you're on a Windows 7, you have to install the drivers. And on a Mac as well, I don't know how, I don't know how supported this is on Mac. If you have a Windows VM or Windows computer, that's preferred. You may encounter some issues when you're running Mac or Linux. So we could cross that bridge if that's an issue for one of you guys. But otherwise, just follow this tutorial on how to set up your Arduino development platform, how to download the correct libraries, and to kind of get you up and started. So I already did this because this is a little time consuming, and I didn't want to spend the recitation kind of going through this specifically, since it's pretty well documented here. So I'm going to switch over to here. And so this is the board I just went through. And then these are boards that we are going to connect to this microcontroller board. So again, each of these boards we bought through Sparkfun. You could find them there and find the documentation for them and find hookup guides for them. And for each of these boards, you have to download a separate Arduino library from that website and install it into Arduino. And again, under the hookup guide, they explain to you how to do that. I already did that just to kind of get us up and running pretty quickly. So, any questions so far? Okay, great.
I'll clarify that the everything that Patrick's showing you today is included in the kit that we're sending out.
Sweet. So I'm going to show you. I'm going to start with one example, and it's going to be making or connecting our environment sensor to the Sparkfun board. So the environment sensor is this little guy right here. The BME, 680. And so it's an air quality sensor. So it gives you some readings, I think on CO2 as well, but also on the humidity and temperature. And so how you connect to this is you use these connectors that Sparkfun already has. They call them quick connectors. And and they're just I2C based. So they have 4 cables. One cable is ground, one cable is power, and the other 2 cables are the clock and then the data. So this is how, you know, one board connects to the other board and gets power and is able to talk back and forth. So I'm gonna connect one of these boards to this quick connector enabled microcontroller board. And there, that's it. It's that simple. And so now we have the sensor connected to the microcontroller. I'm going to connect the microcontroller to my computer. So I'm going to connect to it here. And then now it's powered on. It can connect it to my computer. Your computer will chime and say that it's seen a new device. And I'm going to switch over to, let's see, where is this? All right, let me just move that. Okay. So this is a demo that I pulled. So when you go on Sparkfun.com and go and find the BME 680 development board, there's a library there that you download and import into Arduino. And to import a library is pretty simple. You download the zip file from the Sparkfun website, and then go to include library and add zip library, and then just point it to where it is. You download it, and it's there. And then you can go to File, Examples, and then you'll see the BME 680 pop up, and then they have 3 different examples that you could follow. So this is the first example. What it'll do is it'll set up the communication to talk to the BME 680, and then start streaming or start collecting information from the sensor, and then displaying it on the serial console here. And the serial console is just another communication mechanism from the microcontroller to talk to your computer, and your computer to display that information. And so here you'll see, I'll kind of let you guys go through this on your own time, since this is like a published example from Sparkfun. So they did a pretty good job at commenting it and saying like exactly what this program does and what resources you could use to kind of find out more. But the big things are, you know, when you have an Arduino, a traditional Arduino file, you have the initial function, which is the setup function, and this is only called once. And in the setup function, you essentially set up your system. So if there's any kind of configurations, some kind of protocols you need to start up and set up the data rates and things like that, it's all done in this setup function. And then after the setup function is the loop function, and the loop function, it's exactly what it says it is. It's a function that gets continuously called nonstop until the system runs out of battery or power or whatnot. And so in this example, the USB is started, the serial USB, and that just generally means the UART, the asynchronous communication between the microcontroller and the computer is started, and then it starts printing to the UART. So I'll just load this up. So you go up here to the top left, hit upload, but make sure that under tools, you've selected, you know, there's Sparkfun Redboard Turbo. And for all of you, the COM port will be different. That's just a communication port that it uses, but it should be in parentheses, you know, Sparkfun Redboard Turbo. So anyways, so I'll upload that. Sometimes the upload fails. It'll say failed down here, and what you need to do is on the board itself, there is a reset pin. Oh, let me just switch that. On the board itself, there's a reset pin down here. You just need to click that and then try to re-upload. It's just a little bug that they have. So you can see here, it failed. Oh, maybe you can't see it. Now you can. It failed, and so we need to do that again. So I'm going to hit the reset pin, and then hit upload. And then this uploads the example that Sparkfun wrote. And it just takes a moment. it finished. And then at the top right, you could open up the serial monitor, which is that, again, it's that serial port that we started up. And it displays the sensor values. And what it's displaying is, in this loop function, you could kind of walk through the logic and see, okay, what they're actually printing. And they're printing a few things. So they're printing the temperature, the humidity, as a percentage. So 100% would mean the air is completely saturated, and 0 means it's completely dry. The atmospheric pressure, and then an altitude, which they calculated. And I'm not going to go through the altitude that much, but you could kind of step through like their calculation of how they did that. And they have some kind of calibration constant, and they do walk you through that on the Hookup guide on the website. So I'm not, but the main point is we got the system working. We connected a sensor to the Microcontroller, used their demo to get it up and running, and it's working. The one thing to note is there is a small caveat when using this board. A lot of the examples are going to have, like when they start their serial, or like when they set up the serial port and do all these serial print calls and all that stuff, many of the examples are going to have serial.begin and serial.print. But for this Redboard Turbo, it has to be serial USB. And so when you open up some of the examples, they just won't work. And they're going to say, oh, I have no idea what this serial.begin function call is. Change that to serial USB and it should work. Other than that, that's the only thing that you need to change from using this board to like a traditional Arduino board.
You would have to change that at every place where it calls that serial.
Yep.
Print or whatever. Yeah. So you could do a find and replace for that.
Right. All right.
Sorry, can I ask again? What is the function that needs to be changed? Are there many positions in the same script?
Yeah, so let me show you. So I'll open up an example from the Sparkfun BME 680 sample example from their website called I2C demo. You scroll down and then you look at their setup, and they call serial.begin. Unfortunately, that doesn't work for this board specifically because it doesn't actually have like it uses serial over USB, and so you need to change serial to serial USB, and do that everywhere you see these serial calls from like the serial begin, serial print, and anything else that makes a reference to the serial class.
Got it. Thanks.
Great. All right. So any questions before I move on to the next example? I have a bunch of examples. I'm going to just keep going with different examples until we're done. But if you have any questions, feel free.
So you need to download the two libraries separately for each board, and then you can run the script.
Right. So just to show you, I'll go on Sparkfun. We're using the BME 680 sensor. And there it is. It's the quick version.
You can also go on, we have the bill of materials posted on the Google Drive, so you can look in there and see the exact link.
Right. And then under here, go to Documents and go to Arduino library, and it's here. You could download the zip file, and it will download it. You can't see it, but it already downloaded to my computer. And so this is the zip file. This is the zip file that you go here into include library and add zip library, and you just find that zip file, and then that will install the library, and then you could go to examples and find the BME 680 examples. So that enables you essentially to use this sensor with anything that you design later on. The big thing is you need to install the library beforehand, or the Arduino IDE has no way of actually knowing what some of these variables that you use are, like this class.
Patrick,
Sweet.
does the Arduino IDE have its built-in library manager? So instead of having to download the zip from GitHub, for example, you can.
Yeah. So sometimes you might. Yeah. So
there you go.
sometimes you might find it here, but many times I've been finding it that it's not in the library manager. Especially like this board, I don't think it's in the library manager. There's like the Adafruit version, but I don't know if the Sparkfun version's here. So you could try to find it here, or you could just go on the Sparkfun website and just download it straight from there. I would probably advise that more because you'll be able to ensure that that's the latest copy, and you can follow their guides with that. But again, as Sean pointed out, you could also reference the libraries here, and you might find one that works for you. And these also come with their own examples as well. But yeah, whatever you prefer, I guess but.
Thanks.
Great. So I'll move on to the next example, which is getting the LED screen working. So let me switch over. Okay, so I have this LED screen that you guys are all going to be getting. And so the good thing about the quick boards is that you can just connect one to the other and just form a chain. As you'll see in the problem set, since this is I²C, there is a limit to how long you could go with I²C before things start getting a little bit non-determinate with your system, because if your cable's too long, it's similar to like if you're talking down a long hallway, there's going to be a certain distance where you're not going to be able to understand the next, like the person trying to talk to you. So if you can use short cables, go with short cables. But we're also providing long cables for like applications where where you're trying to put stuff in a box and you need something to be positioned in a specific place or whatnot. So I'm going to use one of the next cables, connect it to our BME 680 board to form a chain, and connect it to this LCD screen. And again, with this LCD screen, you can go on the Sparkfun website, find the libraries for it, download it, and play with it. I already did that. So I'm going to switch over. Here is the next example. It's the micro LED demo example. And I'm going to just load it to the board. And we'll see, hopefully, things working. And again, this is something I didn't write. It's something that you'll be able to freely pull off of the Sparkfun website. Great. And now I'm going to switch over to the capture. And then you can see the screen running a demo. So it's just that easy. Now, of course, this demo really isn't useful for you guys. It just shows you that the system does work. But you might want to do something a bit more custom. Like show some text or show some visualization. And for that, really, again, Sparkfun does a really good job at explaining to you what their OLED library does. So like if you go to so if you run to the board and then go to documents, and then you could find the, actually, I don't know if I'm going to be able to remember where exactly it is, but so this is the board, and somewhere down here, they start referencing the exact library that they use for the OLED. So this is the library. These are the commands. These are all the different things you could change: the contrast, the pixel size, lines. Make rectangles, text sizes, and it's all they kind of walk you through every single function call or everyone that's more commonly used through this example. So you could kind of pick and choose at what you want to use and how they use it, and kind of work backwards and create your own beast. But so this is less interesting for our application. Let's try to get something working with the sensor that we had working in the previous example, using this screen to show some value. So I already built a project for that. So in this project, what I do is a lot of the stuff is pulled from the BME 680 example that I showed you before, like the exact setup files. But what I did is I took bits and pieces from the OLED example that you could pull from Sparkfun and kind of merge them into one. And so what I do here is in the loop, in the function loop that runs continuously, I created this sensor output function. And the sensor output function, what I do is I take one of the samples, and in this case the humidity value. So you could see in the read BME 680 function that I created, I'm taking the humidity value that we find and returning it from this function and passing it to this variable, and then setting this variable to this new function. And then this function, I set the font type. So again, on the Sparkfun website, you can see if you set the font type to 1, it's this pixel size 8 by 16, and set the cursor to the top left. That should be a 0. And then I start printing. The first line I print is this, and then the second line I print is what I pass to this function. And in this case, it's going to be the humidity value. So I'll load this up, and then we'll see what this does. Oh, I need to press the reset button. Everything goes well. It should start displaying something. All right. And there you go. That's the humidity. And so the interesting thing about humidity is when we exhale air, we exhale humid air. So if I breathe on the sensor, you'll see the humidity go up. So a lot of people use humidity sensors for like breath detectors, which is kind of interesting. But you can use it for a lot of different applications where like the humidity fluctuates. You could think of different space applications. I'll kind of leave that up to you and to kind of think about. But yeah, so now we created a project that uses the microcontroller, pulls data from this sensor, and then sends that data through the I2C lines to this OLED screen and shows the data values in real time. And in the example that I made, I sample the sensor once every, or I try to sample the sensor once every 200 milliseconds, so 5 times a second. That's not completely accurate because it does take some time to read this sensor. So in this read function, it kind of goes through all of this stuff, and each function call has some time constant associated with it. Because what it does is it actually communicates to the sensor, waits for the sensor to talk back to it, and then takes that data and then does something with that data. So it's not exactly 5 times a second, but that time constant really depends on your application and what you're trying to get. We can make the system run a lot quicker if we just want humidity values. But in this example, we're looking at all this different stuff, different CO2 values, pressure, humidity, altitude, and stuff like that. I think it's a little bit too much in the weeds here, but what I'm getting at is like if you want to optimize your system so that it samples at a specific interval, then you need to put some thought into some of the delays that could be in that exist in actually reading values from a physical sensor. Okay. Any questions on any of that? I think I went through that quite quickly, so I expect some questions, but. All right. Well, so the next thing that I'm going to show you is connecting the joystick. So going back to here, we have this joystick. The joystick has a couple functions, of course, up and down, left and right, diagonal, but also click. And all of these different actuations or sensory inputs by my finger to the joystick can be read on the microcontroller. So what I'll do is what I did with the previous sensors. I'll take another connector, connect it to the LCD screen to continue our chain. These are polar, so you can't really mess up on connecting it. Great. So that's connected now, and I'm going to run back to my desktop. I had this joystick example again. I went on the Sparkfun website, found the example, and then I modified it a little bit because I have this serial USB function call now. It used to be serial.begin and serial print new line, but I modified it for this specific board. And in this example, you have this joystick instance that's created. This is like like Sparkfun's library that you can actually go on the Sparkfun website. They also reference the GitHub, and you can actually dive into the code even deeper and try to figure out exactly what is in this instance. Or you could just use it, and they just tell you the different function calls that you could use. Or the different functions that are associated with this instance, and just use them as the example shows you. If you don't want to dive too far into the weeds, like for instance, like if you want to create a quick prototype. So again, we set up the serial USB call, the serial USB peripheral, which is how the microcontroller talks to the computer. We print this line that the computer sees, and then we make sure that the joystick can start. So this begin call, and if the joystick does not start correctly, then tell the computer, hey, it's not working, something's wrong. And then we enter this loop function, assuming the joystick works, and we continuously read the joystick. We read its horizontal values and vertical values, and if it's pressed. And so I'm going to load this. Does take some time to load, but great. And I wonder if I have, one second. Let's see if I have, nope, that doesn't work. Oh, great, I have that. So now you'll see, I'll open up the serial terminal, and you'll see the program spitting out these values. And again, it's spitting them out because we tell it to spit it out. We say print the X value, then print the return from this function, get horizontal, and then the Y value, and then the button value. And so you'll see me take the joystick, I'll move it up. You see the Y goes to 0. If I move it back down gradually, you'll see it slowly go back to its starting position. I'll go the opposite way. You'll see it go to 1023, and then slowly back to where it was, and it's 510. And then the same situation for the X and the Y, and then you could do like a circle, and that varies everything. And then the button, if I click the joystick, it goes to 0. And so you could form some logic in your code that, oh, if the joystick is pressed, or if the joystick is moved to a certain location, then do X, Y, Z. And it's really up to you what you want to do. So this would essentially be your input to your system, and your output could be, flickering some lights or moving a motor. It's really, up to you. But that's essentially how you get the joystick up and running. And then the next example will be then fusing the joystick with the environmental sensor that we already used and the OLED screen. So as is customary, I took the BME 680 example from the Sparkfun website, took the OLED example that we wrote, combined them, and then took the function calls from the joystick example and brought that into that combination as well. So you're going to need to get this instance as well as this include a library call, and then also this instantiate this begin function as well. You're going to need to call that in your setup, and then when you just want to know the horizontal, vertical, and the button values, you call that in your loop. So in this new function, or in this new program, I did all that in the setup, and now in the actual program that runs continuously, I check if the vertical is less than 10. So that means if I move the joystick up, if it sees that it's been moved up, then what I want to do is on the sensor output print up, and the sensor output is just a function that I created to write to the LED, to the OLED display. So, and if I don't mess with the joystick, then go into the else, and then just read the environmental sensor and display the humidity value. So let's see that working, hopefully, maybe. Oh, an error occurred. Let's try to reset this and then try to reload it. All right, that seems like it's worked. Okay, so the humidity value is displayed as it did in our past example. But now if we move the joystick up, and this is up in this orientation, this is gonna be confusing. If I move it up, you see that it displays up, because the code that runs continuously is checking if this joystick value is less than 10, which correlates to us moving the joystick all the way up. And if it is, then display up. If I put it back, show the humidity value again. So that's us forming simple logic, taking in some hardware values, some physical actuation that we impose on the system, and respond in a deterministic way. Great. And so the next example are there any questions so far?
I'll ask about plugging those in. When you've plugged in those quick cables, you've done it while everything's powered up. Is that good practice to do, or fine to do?
No, no. So it's not okay. Yeah, great. Generally, it's not good practice to to start connecting anything while the system is powered on. The reason I do it is because you're not supposed to do it. The reason I do is because, for the most part, since I'm reflashing the code after each plugin, in regards to the software, I don't really care what happens, because I reset the software chain anyways. But electrically speaking, if you are playing with the cables and connecting different things to the hardware bus, if you connect it incorrectly, that could be a bad thing. So some connectors, they're really fragile, and some of the metal pieces within them, when you're trying to jam them in, sometimes during insertion, they cross over and create a short. So that's one reason not to have your system powered on when you're plugging things in and out. But for the most part, these are pretty robust. But as Sean pointed out, if you're plugging things in and out, do it first when the system is powered off. And yeah, and as far as these connectors go, they should be inserted quite easily. If you're trying to jam them in and they're not going in, flip them, because they are keyed. So there is a specific orientation that they go in. but yeah, it should be pretty easy. But yeah, to Sean's point, don't plug in things that when they're powered on. But for the most part, you won't necessarily break anything unless you're like really imposing a lot of force on your system. Your software might misbehave depending on how complex your software is, and if you're plugging in different GPIO that you're actually controlling and toggling on and off into something that shouldn't get it while the system is powered on. That's more of a no-no, because this part just like a digital circuit, a communication circuit, and there's some redundancy built in and some robustness, and the power lines are generally pretty low, and the board has some fuses built in. So generally, you won't break these boards, but when you start plugging things into the GPIOs that can only take a certain amount of current or source a certain amount of current, then that's where you need to be a bit more careful. And I kind of allude to that in the P set to kind of look into that a little bit more and try to understand the limitations of powering things through the GPIO. Cool. Okay, so the next example, we're gonna take a slight sidestep from connecting these things in this digital orientation and create an analog circuit. And so to do that, I drew this one circuit here. I don't know if you can see it that well, but what we're gonna have is a motor. It's a little vibration motor that we're providing to you, and an N-channel MOSFET. And so this N-channel MOSFET here, its sole purpose is to isolate the microcontroller from this motor. So this motor requires a significant amount of current, a significant amount of power to actually operate, but that power cannot be seen by the microcontroller, or because it could quite literally burn out the microcontroller. To what I was kind of referring to before is, the microcontroller can only source and sink so much current until an internal fuse pops, or something worse, where like it overheats and it just destroys the controller entirely. So that's the main purpose of this N-channel MOSFET. And so how this works is we have pin 8 right here, and we're going to be toggling it. And so pin 8 is a pin on the microcontroller, and when we take that pin and we control it in software, we could tell it to go either low or high. When it's low in this orientation, when the gate voltage is equal to the source voltage, which is 0, then the system turns off. When the gate voltage is higher than 0, then it's on. So it should be on from like 3.3 to 5 volts, something like that. But the main thing is that you turn this off, you turn this MOSFET off when the pin 8 goes low. Otherwise, it's high. And to kind of visualize this too, since this is a virtual recitation, is I also took an LED and I connected it to this drain as well. I don't know the exact resistance value that I used, but there is a red LED here that will show you when this motor is being turned on and off. Yeah. So here's a circuit. The motor is actually on this box, and I put it on the box so you could actually hear it when it turns on and off. I created that circuit that I just showed you on paper here on this breadboard. This is the N-channel MOSFET. This is the LED with its associated resistor. I'm going to take the ground and connect it to the ground on the board. And so you'll see the board labeled ground. I'll take the power, connect the power to the board, and connect that to 5 volts. Because it's already on. Let me just turn that off. And connect that to 5 volts. Because that's the voltage that we need to power the motor. But that 5 volts will never be seen by the actual microcontroller, because we're isolating it. So this 5 volts will never be seen by this pin 8. And that's important because for this microcontroller specifically, none of the pins on the controller are 5-volt tolerant. They're only 3.3 volt tolerant as its highest. So if you connect 5 volts directly to pin 8, you will blow it. It's just that simple. So yeah. So what I'm going to do now in code.
Patrick, can I just clarify a little bit? The microcontroller that Patrick's talking about, we're not actually talking about that entire PCB, that entire breadboard area. Yeah, I pointed out exactly. It's just that little chip on there. So the 5 volts that we're providing to the motor is not running through there, but it's running through. You can point to the power regulator, but there's another component on that board. It's probably over there. Yeah, that's that can provide the amount of current that motor needs. So it's still all going through the big board, but not through the little chip, which is the brains, or the important part of it.
Right. So if you go on the schematic for this Redboard, you'll see on the schematic the 5 volts comes in through the USB connector that's connected to your computer. It goes through a regulator, which I believe it's this little guy, but I'm not quite sure. It could be this guy actually. And that 5 volts gets stepped down to 3.3 volts, and that's actually what powers this microcontroller. So all the logic in this controller is at 3.3 volts. But this 5 volts is just directly from the USB, and it's never actually used within the microcontroller. So if you connect the 5 volts directly to to any of these pins, you'll blow it. So just keep that in mind, because there is a connection to the 5 volts on here, which we are doing right now. But just make sure you don't connect the 5 volts to anywhere else on these headers, because that could essentially blow your system. So that's like the huge caveat with these microcontrollers, and that's generally how people break them, is connecting the 5 volts to any of the other pins. So yeah, anyways, back to the code.
Sorry, can you clarify the difference between the red wire and the black one?
Okay, let me actually show you. Let me show you this, and let me. Okay, so these boards, this is the microcontroller right here. And so this microcontroller has these pins on it, and each pin is connected to a specific thing within the chip. So if I go to the schematics, you have this microcontroller. The metal pins that I just pointed out are listed here, and each one goes to a different function. And to find out exactly what those functions are, you have to go to the data sheet. And so you'll be doing some of that in the problem set to kind of understand what each of these are. And for these development boards, what many people do is they take these pins and connect it to these larger headers. And these headers just allow you to connect wires to like a breadboard or to another sensor that run directly to your microcontroller. So they run to the microcontroller through these traces. You probably can't see them, but there's like these little traces. Oh, actually, let me switch it really quick to 1 second. All right, and I'm black, and let's change that. One second. I take it you guys just see a black screen?
Yes. Yep.
All right.
Are you just trying to show a close-up of the breadboard?
Yeah, I actually have a microscope.
Oh, okay.
which might
you
be,
might just be able to zoom in on, like, click the image on the Sparkfun website if you can't get the
Yeah.
Mac working.
I'll just do that.
Well, now we see something.
That's the GoPro.
The GoPro.
Yeah. So I'm gonna reset this back up, and then we'll just go. Anyways, yeah, we'll go back to this. Actually, yeah, that could work. So you can see from these pins, you have these traces, and each trace goes to a specific connection on the connector. And you could connect a wire into these holes, and that will connect you directly to these pins. And on Sparkfun, you have each of these pins. They have labels, or on the Sparkfun board, they have labels, and these labels correspond to, on this actual board, in the hookup guide, you will see down here that each of these labels correspond to a specific pin on the microcontroller. So like this SCL pin up here is PA23, and PA23 per the schematic is a pin on the controller, PA23. So that's essentially how you kind of map, okay, this physical pin, where it goes on the microcontroller, and then you go on the data sheet for the microcontroller. So this is the part number, and you find out exactly what that pin does. So after you play with some examples from like Sparkfun and Adafruit for these different sensors and these different inputs and outputs, when you want to create more advanced things and try to really understand the limitations of these sensors, that's when you start going into the data sheet and trying to really understand, what these pins can actually do, what their maximum and minimums are, and how you could better utilize them in your system. So, so that's really what you do after you play with an initial example. Did that answer your question?
Yeah, thank you.
Yep. Okay. For some of these topics, I'm kind of skimming through them pretty quickly because I could probably spend a day just talking about each individual thing. So if there's anything in particular that you're confused about, shoot me an email afterwards or whatnot, and I'll try to explain that better. I'll try to run through the buzzer example really quick right now. I have another example where I take the buzzer and I kind of combine it with everything else we've done, but that's in the similar. But that's not anything novel. So let's try to get the buzzer working, and then we'll leave it there. So where am I? Wrong screen. Second.
I'll jump in and just say if you need to leave, then we're certainly well past the normal scheduled time. So feel free to hop off. And this is being recorded, so I'll post that in the folder later today once I can get it.
Right. Okay, so this last example, we're going to take that buzzer circuit that I just showed you guys, and we're going to connect it to a GPIO pin. That's going to toggle the pin on and off at different rates. So this is called pulse width modulation. And what that really means is that there's an internal circuit in the microcontroller that you'll give it a number, in this case from 0 to 255. And what that means is it's a ratio. I'm toggling this at a specific frequency, and it will be on for a fraction of the time. And so if I put 0 in, then that means it'll be on 0 out of 25 ticks or 255 ticks, which means it's never on. And if I give it 255, that means that it's always on. It's going to be on 255 over 255 ticks. If I do 150, then it's only going to be on approximately 3/5 of the time. And so Sparkfun does a really good job explaining pulse width modulation through multiple examples. I want to just walk you through the simple one here and kind of show you what the signal kind of looks like too. So this example is pretty simple. We define a motor pin, and this the pin's going to be pin number 8. I pulled pin number 8 from the development board. So there's a pin on here that's called D8, which stands for 8. I make this variable equal to 8, just so it's simple through our code, so we know like what the motor pin actually is. I set the pin up to be an output. You can set it up to be an output or an input if you're reading or writing a value. And you need to make sure that the pin can do pulse width modulation. Not all the pins can do it, and you really get that from the data sheet for the actual microcontroller, or on Sparkfun here, this tilde here, this tilde here means that it's PWM capable, that it could actually modulate the output pretty quickly. And this is exactly how like people like fade LEDs to like gently increase and decrease in luminance. And so what we do in this loop is we run through this loop as quickly as possible with the delay of 2 milliseconds each time. And then we write to the motor pin the variable I, and the variable I is incremented from 0 to 255. And then we do it again, but we decrement it. So what we're doing is it's going to be essentially a sawtooth wave. And so we're going to be gently increasing it, decreasing it, increasing it, decreasing it. And so what that will mean is that you'll see or hear the motor and then see the LED increasing and decreasing, increasing and decreasing. And so I'm going to load this up. This might be a little annoying. I don't think it's going to be that loud, but we'll see. Nope, that's not it. Okay, so let me switch over to okay, so you see the LED, and do you guys hear the motor? Yeah, you do. Okay, yes, great, sweet. So this is exactly what I'm doing. So I'm modulating it, and it's you know what? I'm gonna make the delay a bit larger so you can see it better. 1 second. Oh, so that generally happens when you program it. The pin is always in this unknown state, which will turn on the MOSFET. So I'll just round it so that it shuts up. And then we just load the new code on there. So I changed the delay to 10 milliseconds, so it'll be more gradual. And come on. All right. And now it's slower. And what I'll also do is try to show you guys one last thing. So I have this oscilloscope here. An oscilloscope lets you see the voltage changes in a circuit. And so I'm going to just visualize or probe this pin and show you exactly what it looks like. If everything works, and then I'll leave it there. All right. Great. So this is the changing signal, and I'm going to zoom out. Actually, so yeah, so when it's high, it means the voltage is high. When it's low, the voltage is low. That's not the correct level. I need to send that to. All right. It looks a bit confusing, but Okay. So when it's high, and when it's low, obviously. And so you could see us modulating it from 0 to 255. So when we input an integer value of 255, it's always high, and then when we input an integer of 0, it's always low, and you see it now oscillating between the two states from going to low to high. And so this is called pulse width modulation. And in the case for LEDs, the refresh rate of our vision is actually pretty low, which is why that if you do these quick changes a lot quicker than the refresh rate of our human vision, then we see that as a fading, and not necessarily as like we can't actually see these quick oscillations. So it's kind of a visual trick, but that's generally how many circuits do fading of LEDs and trying to change the luminance intensity. But yeah, so I'm gonna turn the motor off because it's pretty freaking annoying. And I think I'll just leave it there since we're pretty well over. Again, this video is recorded, so you guys can review it. If you have any questions, let me know. Actually, if you have any questions now, you could shoot them to me or say them right now, but let me know.
Thank you.
Yeah,
Thank you.
no worries.
Quick question on the frequency of that PWM signal. What's the, how many times is it turning on and off each second?
Yeah, I actually don't know what Sparkfun, what the library, what's the initial. You could change that. There's a way of changing that. I don't know what the stock value is. I'm sure it's like somewhere in the world. It's definitely above 1 kilohertz. But I don't. I could probably. Oh, actually, 1 second.
So that would be in the data sheet, of course.
That won't be in the data sheet. So the data sheet will tell you what the maximum frequency you can use, and that's really dependent on the crystal that your chip uses, which that gets a bit more advanced. But the value that the Arduino IDE uses when you set it, that's really dependent on Sparkfun's library. So when you download the board configuration from Sparkfun, so when you go to the Sparkfun Turbo board library for this microcontroller board, there's presets in there. And so when you do when you set up the PWM, it's a preset frequency that some engineer at Sparkfun set it to, and then you could actually modify that as well. So if you need it to oscillate at a faster frequency, you could definitely do that. But yeah, so it's not in the data sheet. The data sheet will just tell you like what the maximum possible modulation frequency is, and that's usually dependent on how quickly you're running your processor. And I forget what the frequency of this processor is, if it's like 48 megahertz or something. But yeah, essentially, if you want to increase or decrease that modulation frequency, you can do that. There is a function call that you can use, but you just need to Google that one because I don't know that off the top of my head. So yeah.
That's it. We'll let Patrick go. And this is recorded, and I'll make sure it's posted. So last call on questions. Of course, Patrick is available by email, and if there's something complicated, I'm sure he'll set something up for you. Yeah,
I did go through a lot of this quite quickly, so if you didn't understand it or a subset of it, that's totally expected. So let me know if there's anything that was confusing. I could point you to better resources or other resources that explain different specifics of what I explained in more detail. But I kind of just gave a quick overview of running with a couple demos from the Sparkfun website. Great.
Thanks, Patrick.
That's good. Thanks,
See you guys.
Patrick.
See you, everyone.
Thanks, Sean.